Hey, what's up guys? So today Alex and I are going to be talking about rotational dynamics. Just a review on the topic since A, we only have that much time, B, we only have that much knowledge, and C, nobody can beat Mr. Raz. So yeah, credits to Alex's animation skills and her patience in writing the script together with me and putting the video together. Here are the topics we're going to be talking about today. Note that we won't be going in depth about forces, that is pure dynamics, and not really just rotational dynamics. Cool, let's jump right in. There are two ways a ball can move. One way is translational, where the ball simply slides across a frictionless surface. Another one is rotational motion, where we see more often, when a ball rolls around its center on a surface. A rolling ball has both rotational and translational motion, because while it is rotating, it is also moving forwards. What causes a rotational motion? We'll get to that later. For a linear object, a force is what causes an object to accelerate. In fact, force equals the mass of the object times the acceleration of the object. Note that it says accelerate. If there is zero acceleration, there is no net force applied, which means that an object can potentially be moving, just at a constant velocity. Force is a vector, which means that it is positive when the force applied is in the same direction as the acceleration of the objects, and negative when the force applied is in the opposite direction as the acceleration of the objects. Torque is a force applied, which causes an object to rotate around an axis. There are a couple of rules for torque though. First of all, it must be applied at some distance from a point of rotation. Take for example this door. If you apply the force directly towards the hinge of the door, it won't budge. Another rule is that it must be applied with at least one component that is perpendicular to the direction of rotation. An example is that door again. If you push from the side directly into the hinge, the door also wouldn't budge. This isn't to say that the force has to be perpendicular, but instead that there is a component of the force, a tiny bit of it, being perpendicular. The formula for finding torque is the force applied times the length from the axis of rotation to the point where torque is applied, times the sine of the angle made between the force and the surface of contact. So let's compare a few torques. If you have a force pushed perpendicularly 0.3 meters from the axis of rotation, and another force of the same magnitude pushed 0.5 meters away, but at a 28 degrees angle from the perpendicular, which generates a larger torque. Here's another scenario. The same door, but a force of 30 newtons pushed 0.3 meters from the axis of rotation. Another 30 newtons pushes 0.5 meters from the axis of rotation. What must the angle of the second force push at in order to generate the same torque as the first one? Another force pushes at 0.22 meters away from the axis of rotation at an angle of 70 degrees. What must the force be in order to generate the same torque as the first torque? Now back to the two motions. If you apply a force to a ball on a frictionless surface, the ball would simply skid across the surface. This seems hard to conceptualize because we so often see balls rolling. Since a frictionless surface is difficult to achieve, what we see most days are the results of a non-frictionless surface, meaning that friction cannot be negligible. This friction force is what makes the ball roll, in fact, as a ball skids across a frictionless surface and onto a surface where friction is not negligible. Friction applies a force at a distance away from the center of the ball and is perpendicular to this distance, which causes it to roll. Equilibrium is a fun thing, and it makes it super easy to solve problems. Static equilibrium is when the object is not in any motion. Basically, it is just sitting there. Dynamic equilibrium is when an object is in motion, it does not have an acceleration. This is separate for linear and angular equilibrium. An object can have linear equilibrium, aka it's not moving. It have angular acceleration, aka it's speeding up as it is rolling. An example for this is the wheel on a pulley. Sure, it is spinning faster and faster, but its position doesn't move. Solving for force equilibrium should have been already covered in the dynamics unit. So here we're going to be talking about torque equilibrium. Remember, when an object is in equilibrium, there is no acceleration, which means no net torque. This means that all the torques added up in different directions cancel out. Just like how you would approach a force problem, draw a free body diagram for a torque problem. A fulcrum supports the rod at the midpoint, so this point becomes the axis of rotation for the rod. Two blocks of weight 50 newtons each rests on the left side of the rod. One of them rests 10 centimeters from the midpoint and another 25 centimeters away. Another mass of unknown weight rests 17 centimeters on the other side. The question is, what must the weight of the unknown object be in order for this rod to be in equilibrium? Because the rod is in equilibrium, all the forces must cancel out. We first draw the free body diagram of the rod. There are two weights on the left side pointing down. There is also the weight of the rod, which rests at the midpoint. However, we don't need to consider it for two reasons. A, the weight of the rod is at the axis of rotation, and as a result, the force generates no torque. B, the force generated upwards by the fulcrum counteracts the weight. And lastly, on the right, there is the weight of the block of unknown weight, also pointing down. Now you ask, how can the torques balance out if they're both pointing down? Well, we can't consider it by pointing up or pointing down anymore. Because if you push one end of the rod down, the other end travels up. Instead, we use the clockwise and counterclockwise method. In this problem, we'll consider clockwise to be positive. The two masses on the left generate a clockwise torque, so we label it as positive. The mass on the right generates a counterclockwise torque, which we'll notate as negative. Now we do our calculation. Center of gravity is similar to center of mass in that it is the average position of all the parts of the system, except this time it is a measure of their weights rather than the masses. For a rod that is uniform in weight, its center of gravity is precisely at its halfway point. For humans, it is around our stomachs. Many objects, such as donuts and boomerangs, have their center outside their body. But what if there is more than one object, and you want to find their center of gravity? Like if Kermit and Big Bird, for quarantine reasons, wanted to meet up, but didn't want to risk it. Use this equation. If we put ourselves in a coordinate grid, then it'll become clear. Kermit stands 1.7 meters to the left of the y-axis, and Big Bird stands 2 meters to the right, and their masses are 50 newtons and 500 newtons respectively. Then we simply plug the values in.
Who's that Pokemon? It's Magnemite! Magnemite!
To help visualize center of gravity, break down the system into two objects. Think of each object as a magnet and the center of gravity as a little object that the magnets are attracting. Instead of staying in the middle, the center of gravity will be closer to the stronger magnet, aka the object with the larger weight. So let's talk about moment of inertia. This is something that greatly mystified me. Moment of inertia, also called rotational inertia, is a property of any object which can be rotated. It is a scalar value which tells us how difficult it is to change the rotational velocity of the object around a given rotational axis. Indeed, the rotational inertia of an object depends on its mass. It also depends on the distribution of that mass relative to the axis of rotation. When a mass moves further from the axis of rotation, it becomes increasingly more difficult to change the rotational velocity of the system. This is because the mass is now carrying more momentum with it around the circle due to the higher speed, and because the momentum vector is changing more quickly. Both of these effects depend on the distance from the axis. The moment of inertia for a point mass, i.e. a Pokemon rotating around a point, or a hollow hoop, is mr squared, where the m is mass and r is magnitude of the shortest distance from the axis. The moments of inertia for other objects are more complicated than this. You do not need to memorize them. But here is a general list of the moments of inertia of objects. Now that we know what moment of inertia is, we can apply it to Newton's second law. Newton's second law states that force equals mass times acceleration. To clarify, the acceleration here is linear or tangential acceleration. And from rotational kinematics, we know that tangential acceleration equals the radius of the rotating object times the angular acceleration. Plugging that into our formula, we get F equals mr alpha. Very cool. But what can we do with this? Well, remember that torque is F times R. So if we times both sides by R, we get torque equals mr squared alpha. Oh, that mr squared looks familiar. It's moment of inertia. Substituting I with mr squared, we can see that torque also equals the moment of inertia of the object times angular acceleration. Rotational work is simple. The work done by a constant torque in turning an object through an angle. The equation is work equals torque times theta. Remember torque equals force times radius from the previous slide? Well, work equals force times the arc length, and the arc length equals r times theta. So we get work equals torque times theta. So there is something back there that you should crop out. Thanks, yeah, thanks. It also takes energy for an object to rotate. Its formula is 1/2 I omega squared. The omega is the angular velocity of the object. The I is the moment of inertia of the object. This is a very boring slide, but don't worry, the next ones are really fun. Now we must make some comparisons between the movements of some objects. Let us place a cube on a frictionless incline, and a solid sphere, a cube, and a solid cylinder on 3 other inclines, where friction is not negligible. The presence of friction will allow the object to roll. Upon release from the same height, which object will reach the ground fastest?
Flawless victory. Choose your destiny. Choose your fighter.
This is a very typical conservation of energy problem dealing with rotational kinetic energy. Here there are 3 energies that play a role in the entire mechanical energy of the object: gravitational potential energy, translational kinetic energy, and rotational kinetic energy. The translational kinetic energy is the formula you're used to, 1/2 mv squared. An object that is both rolling and moving has both translational and rotational kinetic energy. As a result, comparing the inclines and conserving the energy, we see that the cube has the most of its gravitational potential energy converted into translational kinetic energy. All of the others have some gravitational potential energy transferred into rotational kinetic energy. But how much? The less the rotational kinetic energy means the more the translational kinetic energy. And the difference is in the moment of inertia. The moment of inertia for the hoop is mr squared. The solid cylinder, 1/2 mr squared. The solid sphere, 2/5 mr squared. Therefore, more GP will be transferred to rotational kinetic energy for the hoop than to solid cylinder than a solid sphere. So the solid sphere will hit the ground after the cube, followed by the cylinder, and finally the hoop. The formula for angular momentum is I omega, where I is the moment of inertia for the object, and omega is the angular velocity of the object. However, for point masses, there's also another formula you can use, mvr. The derivation of the formula is also quite simple, since the moment of inertia of the point mass is just mr squared, and the angular velocity from rotational kinematics is the tangential velocity divided by the radius. We substitute these expressions into the equation and get the result of that for a point mass. If linear momentum is conserved for a system, then the same can be said for angular momentum. As a result, if you change any of the variables on one side and keep the other constant, you change the variables on the other side. An extremely typical example of this is an ice skater. How are they able to spin faster and faster on the ice without outside forces? Remember that when they start spinning, their arms are extended outwards. That means that they have a certain radius for moments of inertia, which is mr squared. When they bring their arms in, they are decreasing their moments of inertia. That means at a certain initial angular velocity and moment of inertia, the new moment of inertia is lower, and to conserve momentum, the angular velocity has to increase. So what are you going to do when you see swipe with the angular momentum coming your way? Do not fear. Split the question into two parts, initial and final. Any part of the system that is moving at first is considered to be part of the conservation of angular momentum. Anything that is moving at the end is also considered to be part of the conservation of angular momentum. Simply add the components up. If an unmoving object is added to a moving object, simply don't include the stationary object at the beginning and add it at the end. Here's a weird concept. Does an object traveling in a straight line have angular momentum? Well, yes. Imagine this rod fixed at the left side. So when hit, it rotates around this axis. Now a lump of clay comes, traveling in a straight line, and hits the rod. After sticking to the rod, the clay rod system rotates around the axis. You can see that the system has angular momentum, which is transferred by the clay. I mean, where else will we get the transfer from? But did the clay have angular momentum in the first place? This is a curious question. The easy answer is that the clay, which is moving, provides a force on the rod, which also provides a torque. And a net torque is what causes something to rotate and have angular momentum. Let's label our variables. Let's say that the clay has a mass 0.5 kilograms. It also has a velocity 2 meters per second. What about the distance? Here we aren't calculating the radius of the clay, but the radius of the rotation. We're also tempted to use the distance from the clay directly to the axis of rotation, even though it hasn't hit the rod yet. That is also wrong. The distance, as it turns out, is the distance of closest approach from the axis. Let's just say that the radius is 0.75 meters. Now we plug the numbers into the formula MVR and get our results. Here's a more conceptual problem, and it may cause you to overthink. I'll read the question out in case it's hard to see. The figure above shows the 3 stages of a dive performed by an athlete. During the dive, the athlete completes several rotations in midair while traveling from the platform to the surface of the water. Figure 1 shows the athlete just after jumping off the platform. Figure 2 shows the athlete rotating in midair. Figure 3 shows the athlete about to enter the water. The first question asks, in a clear, coherent, paragraph-length response, explain why the athlete's angular speed increases between Figure 1 and Figure 2, but decreases between Figure 2 and Figure 3. The angular speed of the diver increases between 1 and 2 because the diver reduces her rotational inertia by decreasing the radius of her rotation from a rod shape to a spherical shape. This mass is constant, so a decrease in R leads to less inertia. The opposite happens when the diver opens herself up from 2 to 3. The second question asks, is the rotational kinetic energy of the athlete in Figure 2 greater than, less than, or equal to the rotational kinetic energy of the athlete in Figure 1? The rotational kinetic energy is larger for Figure 2 because as the angular speed for Figure 2 increases, as shown in part A of the question, the rotational kinetic energy, which is 1/2 I omega squared, will increase. There is also a transfer of gravitational potential energy from the height jumped off at Figure 1, which has literally no kinetic energy to begin with. That is transferred into both translational and rotational kinetic energy. As a result, the rotational kinetic energy will be larger at Figure 2. As seen from above, a playground carousel is rotating counterclockwise around its center on frictionless bearings. A person standing still on the ground grabs onto one of the bars on the carousel very close from the outer edge and climbs aboard. Thus, this person begins with an angular speed of 0 and ends up with a non-zero angular speed, which means that he underwent a counterclockwise angular acceleration. The carousel has a radius of 1.5 meters, an initial angular speed of 3.14 radians per second, and a moment of inertia of 125 kilogram meters squared. The mass of the person is 40 kilograms. Find the angular speed of the carousel after the person climbs aboard. So let's get to this. We consider a system consisting of the person and the carousel. Since the carousel rotates on frictionless bearings, no net external torque acts on the system. Therefore, its angular momentum is conserved, and we can set the total angular momentum of the system before the person hops on equal to the total angular momentum afterwards. The initial angular momentum of the carousel is I carousel omega naught, where the I carousel is the moment of inertia of the carousel, and omega naught is the initial angular velocity. After the person climbs aboard, the total angular momentum of the carousel and the person is I carousel omega final plus I personal omega final, where the omega final is the final angular speed of the carousel and person. The person's moment of inertia is mr squared since he is at the outer edge of the carousel, which has radius r, which represents a point mass rotating from its edge. Applying the conservation of momentum leads us to this calculation and answer, which is 1.83 radians per second.
Alright, so what I'm going to be doing here is using Beyblades to physically show some of the points that we created in our slides. Now, if you don't know what Beyblades are, I'm going to have to quote Sal Khan and say,
You might think about trying to lead a more rich and fun life.
the first point that we made was that there's two different types of motion, translational and rotational. Now with this right spinning Beyblade, you can see that it's going around the arena translationally, but it also has its own rotational motion. Now if I were to compare that with a left spinning Beyblade, so here's our right spinning, here's our left spinning, you can see that they travel in opposite directions. The left spinning tends to travel more clockwise, while the right spinning tends to travel more counterclockwise. Now this is pretty cool because the right spinning Beyblade and the left spinning Beyblade travel in opposite directions, which means that the direction of their rotation also affects their direction of travel. Now, to create rotation, we had to have a torque, right? If we look at the launcher piece for the Beyblade, it spins in one direction. It has 2 points, 2 little prongs right here that stick into the Beyblade. We'll say it's at a 90-degree angle. And so, in our formula, it should look like this, right? And in the diagram here, you should see that the 2 points are actually creating torques, not on the very edge of the Beyblade, closer to the center, but in the same direction. And that's what causes the Beyblade to spin. Now, what about equilibrium? I'm going to actually show you right here. I'm going to use this launcher here, and hopefully this works. So, in a moment, it should slow down until it gets to a point in the center where it doesn't really move anymore. And right now, we could say, well, as soon as when it was on the launcher, when the launcher was still spinning, there was a force applied to it, right? Now, here, you can say, well, there is no force, but it can't be in equilibrium because it's decelerating. It's decelerating because of friction, right? Where in real life, we got friction. And so even though there's no acceleration, there's deceleration, and that's not in equilibrium. So what about the center of gravity? Well, we're actually going to do a little experiment later, but I just want to talk real quick about 2 systems we can have. We can have the Beyblade Earth system, and we can have just the Beyblade system. With the Beyblade Earth system, we're talking about the Beyblade in regards to its height. So I have 2 Beyblades here. This one, as you can see, when it spins, it will be much higher off the ground than this Beyblade here. And now why is that important? Well, if we look at the Beyblade Earth system, the center of gravity for the shorter Beyblade will be more stable, right? It's closer towards Earth. Now, if we look at the Beyblades themselves, we can talk about the center of mass. And this is where a really cool thing comes in. I can do this right now. So Beyblades, they're made of many parts. This is the metal wheel. Now, this one is a perfectly good, symmetrical metal wheel. But here we have the same metal wheel, except it's missing a prong, and I don't know how I broke that. That's probably like a few years back, but I'm gonna put the Beyblade parts onto here, and then we can compare and talk about their center of masses and how it affects their spin. Alright, so with the normal unbroken Beyblade, the center of mass should relatively go straight through the center, right? That's where the tip is, and that's how it's spinning, through its center of mass. But with the broken Beyblade, if we take a look at just the wheel itself, the center of mass, instead of being at the very center, should be shifted up a bit. And that's a problem because where you're spinning, your tip, is still in the original center, not your newly shifted center. And so I can show you guys how that affects the spin right now. Here is the regular. Here is the broken one. Now, even though this one was able to knock this one out, I don't know how, that was fantastic. But you could see that it wasn't spinning stable at all. It was wobbling about as it was rotating and as it was moving. And that is, again, because of the change in the shift of the center of mass. Awesome. Now, we're going to talk about the moment of inertia, because when you battle with Beyblades, you want to win, right? And moment of inertia really depends on the mass and the radius of the Beyblade. So actually a better comparison for me to do here is between these two. This Beyblade is heavier than this Beyblade right here. And they have different radii. So this one is heavier and has a larger radius. Theoretically, it should have a higher moment of inertia, which means it'd be harder for this Beyblade to try to knock this Beyblade out compared to the vice versa. So we're going to do that right now. We're going to try. We're going to have a little battle. Except I don't have one of those double launchers, so I'm going to have to launch them in one by one. So we can see that with each collision, not in the beginning, you'll see closer, it'll be a better demonstration, but every time they collide, they're also losing kinetic energy, right? It's an inelastic collision. The loss of kinetic energy, also with friction, causes these two to slow down, and this one actually won. But that's pretty much because I spun it second after this. We also have like lots of other like Beyblade nerd stuff going on with the tips. However, you could see that with each collision, there was a loss in kinetic energy and speed. Now, if we were talking about momentum, the heaviest Beyblade should theoretically win, right? Now, we didn't see that because this Beyblade won, and that was, again, human error, because I can't spin the two of them with the same force at the same time. We're going to try that again, though, just to see. And this time we're going to be thinking about momentum and their collision with momentum. Alright, so this time I'm going to be spinning the smaller Beyblade first, and we'll see what happens. Alright, what if I add a super light Beyblade? You could see this is where the center of gravity comes in. This one is lower to the ground. This one is higher up, and it lost some energy already due to the collision from the first Beyblade. So the second Beyblade here, it still didn't win though. Why? Because this Beyblade, the heavier one, with a larger radius, it still has the heaviest moment of inertia and momentum, right? So, this is why in Beyblades, people like to buy heavier ones. Now, again, there's so many human errors that can go on with this. I was just talking about some like cool stuff, but don't think about it too much. I hope that helped you guys out with a bit of more like real life conceptualization. And so, yeah, thanks for paying attention. Thanks for not falling asleep.
Buddy, I am the Dragon Warrior. Ah.